All right, we are recording right now.
All right, awesome. Well, why don't we go ahead and get started? And if anybody jumps in late, they won't miss too much of the technical stuff. I do want to apologize. I have a bit of a cold, so if you guys can't hear me or don't understand anything, because I have a funny accent anyway and a cold, then just pop up in the chat or jump on the line and say something, and I'll go back over it. I'm pretty excited to be bringing you this webinar today on how to do neural networks in R. Neural networks, I think, are one of the coolest things in machine learning and in data mining and in predictive modeling that we have today. They're so flexible, and they can really solve anything from relatively small, easy problems to really, really complex problems. Some of these pictures here are examples of what happens when you use a neural network backwards, which is really interesting, right? So Google put out a paper on their research blog about how they use neural networks for image recognition, which is one of the things that they are very, very, very good at. And if you, instead of giving it a picture and asking it what's in the picture, if you say what's in the picture and then ask it to draw a picture, these are some of the things that it comes up with. So there's an animal and a fish and a banana and a measuring cup, ants, and it really comes up with these very cool sort of trippy images, which is really interesting. And neural networks are used in a lot of other applications as well. Speech recognition, self-driving cars, and they are the foundation of what you've probably heard of as deep learning. Deep learning is really a reference to the number of hidden layers within a neural network. So a deep learning model is a neural network that has a lot of deep layers. And what makes them so flexible is, we'll try and give you an example of it here. So if you think about this as a linear regression, right? If we did a regression on these points, this being obviously using X to predict Y, and we drew a line of best fit through it, it'd probably go something like that. What a neural network gives us the power to do by using the hidden nodes is adjust this line to go like this. And then we'll create a second line, right? And then we can put our second line through the rest of the points like this. And depending on where we are on the x-axis, right, we can then use a different one of these to make our predictions, which makes the model itself a lot more accurate. Sorry, my bottom line's off here. There we go. It's going to make the overall predictions a lot more accurate, right? Because we've got a better representation of what the function actually is. In this case, it's sort of L-shaped. And they do that by performing many, many different regressions at the most basic level. So we take all of our inputs and then we run them into the first hidden layer. We have at least one hidden layer, sometimes two hidden layers of neurons, then into a second hidden layer, then into what's called an output layer, where we have one or more neurons. And each of these hidden neurons is basically a regression of everything within this input layer, right? So we have different weights for each of these input nodes into this first hidden node, and then different weights for each of the input layers into this second hidden node, and so on and so on and so on. And then when we get to the second layer, this top hidden neuron has different weights from each of the neurons in the first hidden layer, and so on until we get all the way to the output layer. And because we're doing that, because we do so many different types of regressions, that's what gives us the power to model functions that might not necessarily work with a simple linear regression model, but they work very well within a neural network. So the question is, with that basis in mind, and we'll take a look at these maybe as we go through some of the examples, is well, how do you do that in R? So I have an example script here for you. One of the things that I do want to stress with this thing is that I do a little bit of data pre-processing, as you'll see in this script. And the reason I left that in there rather than doing it before we get to the script is because for neural networks in particular, data pre-processing is really, really, really important. If you think about our picture here, if one of these input layer nodes has a value that's significantly higher than all the other ones, right? Then when it gets put into this first hidden layer, that value, that really high value, tends to overpower or overweight any other values in this hidden layer. So for that reason, we want to make sure, and you'll see we do as we go through the script, you want to make sure that no one particular variable has a huge range versus any of the other variables. To do this today, we're going to use a package called Neural Net, which is, whoops, I deleted it. We're going to use a package called Neural Net. If you don't have it installed, you can just install packages and Neural Net. I also put a link in here to the documentation. There's a couple of other very interesting things that this package does, not other than build neural networks, right? That's what it does. It builds neural networks. But might potentially be the wrong documentation, but I will check on that. But there's a couple of other graphing functions and things like that it does. So there's a couple of other graphing functions that it does, which is going to help you get under the skin of your network and exactly how it's behaving, what it does, how it trained, which is always really, really interesting. We can, if you guys are interested, we can talk a little bit about how neural networks train, which I think provides some context for why we do things the way that we do and why we try different combinations of parameters to try and get them working. So the data that we're going to use is the same data that we used in the linear regression WebEx. So those of you who watched the video or who attended that one will be somewhat familiar with it. It's basically a bunch of metrics about students that took a math class in Portugal, as it happens, and it has a bunch of sort of demographic and situational, shall we say, data about those students. So it's got quite a few columns, which makes it a good candidate for this. A lot of factors, some integers, but you can see, so there's 2 different schools involved in the study, what their gender is, their age, the address. Address is really whether they live in a rural or an urban neighborhood, their family size, their parental status, so whether their parents are divorced or whether they're together, mother's and father's education level, their jobs, some other various things, right? So then travel time and study time, whether they get a supplement for school, whether their family gets a supplement, all of these things that might give us some insight into how well the student does in the course. And what we're going to do is we're going to try and predict these G1, G2, and G3 variables down here at the bottom. And we're going to use G3, which is the grade for the whole course. So grade 1 is the first midterm, and then G2 is the second midterm. G3 is the combined grade for the whole course. And that's what we're going to look at using a neural network. We already did it a little bit with the regression model. It wasn't particularly fantastic, but so we should get better results using this. So let's go ahead and take a look at the data. Excuse me. As we look through it, you'll see most of these are within fairly small ranges. But there's a couple that we might want to look out for. First of all is age, right? Age has quite a big range. The maximum value in there is 22. And as we talked about, we want to make sure that we scale our variables correctly so that we don't overpower the network when we begin to train it. The other one that is particularly significant as you'll see down here, is absences. Absences goes all the way from 0 to 75, so it has a huge range on it. And we want to make sure, again, that we don't end up just making predictions based off absences. I will show you how to scale that. There's a really easy way to scale some of these variables as we go through. Absences, I tried it without scaling it intentionally, and it actually ended up with one of the fairly common errors which neural networks have, which is that it came out with the same prediction for everybody. And we'll touch on a little bit why that happens as we get through the courses. So the first thing we're going to do is just a data pre-processing step. So we're going to take all these binary variables and encode them as ones and zeros. R does do this behind the scenes, so if you just give it a factor variable, it will actually store each level of that factor is a different number. I like to do it this way because it gives me control and consistency over which, whether yes or no is stored as a 1 or a 0. It's probably not necessary, but it makes me feel better about myself. So, whoops. There we go. So, we've converted all of these. So, activities is now activities.num, and then nursery is nursery.num, and higher is higher.num, and so on and so on and so on. And then we're going to do some scaling of the variables. So we're going to take absences, as I said. Absences is the one with a maximum of 75 and a minimum of 0. So a big range in there. And we're going to divide it by 15. The reason we're going to do that is because it brings it back down onto a more reasonable scale. So it's going to be 1 to 5. And that 1 to 5 scale is similar to some of the other variables that we have in the data. So that's going to help us, again, use it to make better predictions without that number overpowering everything else. You can, if you want, investigate some packages that will do this for you automatically. All they basically do is this sort of thing, so they scale it down. You'll see a lot of items. So if we wanted to do age, for example, if we wanted to scale that back, you can take the age, subtract the mean of age, and then divide this whole thing by the standard deviation of age, which I can't remember the formula for. There we go. And then what this will do, here, we'll just run this side of it first. Whoops. So teach me not to type my commands in before we get too far into it, right? So what this does is, this is the most common method for standardizing and scaling variables. This is going to give the age column a mean of 0 and a standard deviation of 1, right? So you can see now, instead of having ages from 15 to 22, what we've got is ages where it's the mean, it's 0, where it's below the mean, it's -1. And then we have a few that are positive. There's at least one student in here who's 22, so we get a 3.372. This, again, helps scale that variable to make sure that it doesn't overpower anything else because it has a different range or because it has a different maximum or minimum. And then we're going to do the same thing with the targets. So these targets are the grades that the students got for the final course. Each grade is out of 20. So now, basically, instead of it being out of 20, we've just converted it to be a percentage for the final course. So let's take a look at the data and how that changed things. So you'll see, if we go up to age, first of all, you'll see that the mean is 0, as we talked about, and then it has a standard deviation of 1. So there's values both above and below 0. The other ones that we changed were these variables ending in .num. And in most cases, you'll just see that the maximum is 1 and the minimum is 0 because they were all obviously 1s and 0s when we encoded them. And then absences here, we've scaled back so that the maximum absences, number of absences in air quotes, is 5 instead of being 75. So all of these variables are now in a better place. So what we're going to do is, this is another trick that I used during the linear regression WebEx. We're going to create a list of variables that we want to keep. These are all the numeric variables, so they're all the ones that we scaled. And they're also all of the other numeric variables, and then there were a handful of variables in the data that were already numeric. So we're going to keep a hold of those two, and then we're going to keep our target. The target is right here at the bottom. And then instead of typing this out, right, because you could just say data, comma, and then all of these names, but that's kind of a pain and it's kind of messy. And if you have them used in multiple places, you have to change it. So you can use syntax that's similar to SQL, if you've ever used SQL, and just say, I want all of my data where the names of the columns are in this list of variables, or this vector of variables up here. And then we can say, I want the same thing, so I want all my data, but I want it to not be all of the, whoops, I don't want to move that, where the names are in this list of keep variables. And then you'll see if we look at the summary of the first one, here's all the numeric variables. And if we look at the summary of the second one, we have a bunch of factors in here, and then we have a bunch of stuff that I was looking at. It was either too many variables or is one of the targets that we're not going to use. So that's a really sort of compact way of keeping things tidy in the code, which I find makes it easier to read. And when it gets more complicated, you're able to change this list of variables that you want to keep without then having to go into each function and be like, oh, I got to change this one, and then inevitably you miss one and something breaks and it won't work, and it's very frustrating to find out where you changed it. All right, now we're going to create the training and test sets. This is exactly the same thing that you've done before. You'll see again, we're just using a 1 and a 2 as an integer, and setting the 70% to our train set, and then 30% to our test set. Again, and keeping only the names, keeping only the columns that we have listed in our keep variables list up here. So let's go ahead and do that. All right, now one of the incredibly annoying things about the neural net package, it's one of its quirks, you might say, but it's one of the more frustrating quirks, is that normally, right, in other equations, you can put in a formula as we could say, right, G3 given everything. Unfortunately, neural net, for reasons best known to the creators of neural net, doesn't accept that as a valid formula. It returns an error. If that happens, all you have to do to fix the error is just type out all of the items in the formula, right? But that's, let's face it, right? That's a ginormous pain in the backside to go through everything and then type every name from the thing in here. So what this formula does is it just takes all of the names in our training set that aren't the target being the variable that we're trying to predict, so G3, and then it puts them into a list that looks exactly like this, and then it tags the target variable on the beginning. So if we run those, and then we look at my formula, you'll see what it's returned is exactly the same as this. So it's returning exactly the same thing as if I had typed it out all by myself, but I didn't want to type it out all by myself because it's a lot of typing and I'm very lazy. So we have this other way of doing it. And you can use the same thing too. And again, that way, if you change the type of columns or you change the names of the columns in your training set, you don't have to make adjustments in this long list of variables down here. You can just continue to run the code through as you were before, and it will automatically include the correct variables in the formula. If you don't want to do that, as I said, just type it out. It'll work perfectly fine. All right. Now, training our neural network. So, as we talked about yesterday, neural net, the function, has a huge number of options to do all sorts of various things, and they all have good uses. But for the most part, the ones that you are going to want to play with are the formula, so the variables that you put in, and the number of nodes in the hidden layer, which is the hidden argument up here, and whether you want a linear or logistic output. In this case, right, we're trying to predict the score that they got, the score that our students got on that final exam. So we're looking for a regression output. So we're going to use linear output equals true. If we were looking to predict whether they passed or whether they failed the course, which we will do a little bit further down, you'll see that we have linear output set to false. There's also some other things in here you can change to do with how the weights are initialized. And one of the reasons that we do that is because if we want to change the weights or change how we move about our error space, as it were, and I'll explain what I mean by that in a second, we might want to adjust some of these options. So I found a whiteboard, which I now can't get to because the thing's in the way. There we go. So here's what we're going to work with, and feel free to get all chatty with me if you don't understand what I'm on about. But here's what we're going to do. So we're going to look at how a neural network trains itself. So this is our y-axis and our x-axis, right? And this is error, right? Oh, good handwriting. And this is the weight, or weights. Just imagine we're doing this for a single weight. Just leave that as W. Now, it might be that our error space looks something like this, right? So we're going to go from here. We'll start up here. Maybe that's far away. We're going to go down a bit. Now, that looks pretty good, but then we go up a bit. We go down, and maybe down a bit more, and this way. And so what this means is that for each of these weights, right, this is what our error value is, somewhere along this curve. So when we have a weight here, that's our best network, right, is when we have a weight about here. Okay. We randomly initialize these weights. Whenever you start a neural network, all of the weights, all those connections between nodes are randomly initialized. So it might be that when we randomly initialize our weights, we actually end up with a weight here. Okay? And the way neural networks train is they say, okay, well, here was what my error was. I'm going to calculate which direction I need to change my weight in order to make it better. So in this case, we're going to move our weights in this direction. And we're going to do it in small steps. So you might move it that way. And then we're going to move it this way. And then we end up right here. And when we try and move the weights this way, it gets worse. And when we move it this way, it gets worse. So our network thinks that this is the best possible spot for the weight, which of course it's not, because now we can see that over here there's a better weight, but it's hiding. So one of the things we can do is as we change each of these, how we randomly initialize the weights, right? We're going to randomly initialize the weights in a different place, and then maybe we end up with a random initialized weight that's over here. We can go this way, and we can go this way, go this way, till we get to this spot where it doesn't matter which direction we move in because this is the best one, so we go up here. This is the best one, so we go up here. And we end up with a weight in the optimal spot, which is down here. Spotting whether you're in this spot or in this spot is tough, And that's why it's worth running these neural networks with different random weights at the beginning so that you can sort of play them off against each other, as it were, and try and determine whether one starting spot is better than another starting spot, or whether you might want to use one network because it actually have better error, even though it doesn't really seem to have better error. It's just because of the different seeds you gave it. So that's one of the aspects of training neural networks that you want to bear in mind as you go through some of the material here. All right, so back to our sets here, and that's why. So the error is why some of the weight initialization options in here are important. Some of the other thresholds in here that you see are important if we go back to our whiteboard because they determine the size of the step that it takes with each change. So it might be that even though we have weights over here, we can take a big step and end up down here, which is good. But then the problem is we might take another big step and end up all the way over here, and the steps are so big that we never actually get to this this optimal weight down here. We end up somewhere up here. So that's what all of those options do. The good thing is, for the most part, all of these options are not things that you need to mess with too badly. Usually you can just change the seed and that will end up solving whatever issues you have with ending up in a local minima. I wish there was a way for us to visualize this type of thing to see whether we'd ended up in a spot like this, but unfortunately there isn't a good one. Anyway, so we're going to train a neural network, having gone on for half an hour without ever training anything. And it's going to be a network with 10 hidden layers. 10 hidden layers. One hidden layer with 10 neurons in it. I have about 20 variables, so 10 should be fine. And it trains pretty quickly, which is a good sign. When I was having trouble getting this to work yesterday, it would take ages to train, and then I would inevitably know that it was going to go wrong. So that's good. And then we're going to take a look at the model, which prints out enough output in this particular case to take up all of the real estate in the R screen. So literally, I can't even see the command that I typed in because it's all been taken up with this model details. But the nice thing about that is that we can then run through each of these and look at what we did to call it. So the call is going to be the formula that we used to create the neural network. We can take a look at the response variable, which is the target variable that we're trying to predict. We can take a look at the covariates, which is just a fancy name for all of the data that we use, the training data. We can take a look at the variables. So the response variable in this case is G3, and the target variables are all of the variables that we put in to try and make the prediction. Net.result shows us the predictive values. In this case, I truncated it as we did in the exercise instructions so that you're only showing the first 10, otherwise it's just an enormous list. We can also show the weights of the neural network. This is where it gets kind of interesting, right? Because what we're looking at here, you see these are labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the weights for, try and bring these up together. All right, so there we go. So these weights are all of the weights for all of these connections between the input layer and the hidden layer. So our first node, this one at the top is the intercept. So that's the mx plus b value, that's the b value. And these are all the coefficients that we use to tie this one. So this would be our first node, tying it to this first node. This is the second one that ties to this first node, third one that ties to the first node, etc., etc. Then we move on to the second node. So we have the intercept is this first value. Second value is what ties this node to this node. And then the third value is what ties this node to this node. Sorry, this node to this node. And then we've got the third value ties our third input node to the second node, and so on and so on and so on, all the way down until we get to now second layer. You see we have 11 weights. So this top weight again is the intercept, and then each of these ties, this is the first node in the hidden layer to the output, second node in the hidden layer to the output, etc., etc., etc. So that's how you interpret all of those different numbers and what they mean. Here, we'll make this big again. There we go. All right. We can also take a look at, excuse me, what the starting weights were. So these are the randomly initialized starting weights that we used. Again, I wouldn't try and examine this for any evidence of what we looked at on the whiteboard, but sometimes it is helpful to know. You can also look at, if you want, the training error in some of these numbers after each of the, well, this is not actually after each of the steps, but you can look at the error after each training step. This is showing you the connections. This is showing you the connections between each hidden node, right? So this is saying the intercept to the first layer hidden 1 is this value. Age to the first layer hidden 1 is this value. Mother's education to the first layer, first hidden neuron is this value. So if you wanted to, you could take this information and you could hand code exactly the same neural network that you've built by giving the appropriate weight as calculated here to each connection. So I saw somebody had a question here. Let's see. So the nodes themselves are, yeah, they're not necessarily, they are basically, they all perform the same thing, but with different randomized starting points. What differentiates them is, okay, think about this, sort of the path that something takes, right? Let's go back to our diagram here. Oops. So the nodes are connection points. So if we take what's in this neuron up at the top here, and then it has a weight of 1 into this first one, and then a weight of 1 into the second one, and then it comes out into this neuron with a weight of 1. So each of these pathways between the neurons is worth 1. But let's say if it goes to this neuron, it's only going to have a weight of half. So this pathway has a weight of half, and then this pathway has a weight of 1, and then this pathway has a weight of 1. So instead of it being 1, 1, 1, 1, you multiply all together, so that comes out as 1. It's 1, half, 1, 1. So it only comes out as a half, because it's taken a different pathway to get to the output. If this is also worth a half, right, then it's 1, half, half, 1. We'll call that 1. So it's then taken 1 times a half times a half, so it's worth 0.25. So it's not necessarily that the neurons are different, right? It's the weight of the pathways between them that's different. And by looking at those pathways, you can tell sort of how much weight a particular item has. If this has a heavy weight into here, and this one has a low weight into here, and this one has a heavy weight to the output, not as easy to show on this with 2 layers, then you might conclude that these are more important variables for this particular function than some of the other ones. Does that, Tom, does that answer your question a bit? All right, good deal. So now I've bored you to death with math. let's talk a little bit through how we can evaluate what this came out as. Now, as I talked about, right, so we are using a linear output. So one of the things we can do, I skipped the command. You can also plot the neural network, which gives you this fancy view here. Mine's quite a big network, and it does have the weights of each pathway. So Tom, this is what we were talking about, right? You can see through here what the weights are for each. Well, frankly, you really can't on this one because it's a bit too small. But there you go. So this pathway for this top neuron in the hidden layer, so the output is 0.3067, and then each of these neurons leading into that also has a weight associated with it. So you could look at that, and then you could say, well, for age it goes over here, and you can look at the average weight for each pathway and get a sense of which variables are having the biggest impact on the function, just by following the pathway that they take through all of these neurons. Let's make some computations. Let's make some predictions. So we'll create a prediction. One of the things that you'll notice is that when you predict, instead of using the predict function, you use the compute function. And then when you get your predictions, you actually have a list of several items. It's actually a neural network object, as it were. So we want to get in there and we want to look at net.result. If you remember up here when we looked at net.result, that was the predicted weights that we got out of our network for the training set. So when we make a prediction, net.result is the results for the test set in this case. So all I'm going to do is I'm going to take that preds1 object and then I'm going to convert it to just be what the net result is, because frankly I don't really care about the rest of the stuff for the test set. I'm also going to multiply it by 20. If you remember, when we scaled the variables up here, we divided it by 20 in order to reduce the scale. So now we can expand that scale back out again. So it's on, again, the 0 to 20 scale instead of being on the, whatever it was, 0 to 1 scale that we had it on before. And then we can jump in and take a look at a scatter plot of our predicted results. And you can see that it's somewhat successful, right? You could sort of draw a positive line through that, but we're really all over the board. And we do have a big cluster of stuff in the middle here, round about, what's that, between 1 and, around about 10. So we're predicting the average for everybody, which is not particularly good. And we also have some phenomenal scores up here, 50, 40, 30, which is good because you can only get 20 on the test. So we'll just assume they were going to get maximum marks. Even if they did get maximum marks, that's not very good because we predicted they get a 50 and they only got a 10. So that's not a particularly impressive network. But what we can do is we can change the way that we train it. We can change the architecture of the network, the architecture being the number of hidden layers and the size of the hidden layers, in order to try and better predict what our output is. In this case, we're just going to make it bigger. So we're going to take all of the same data that we had before, the same training data. We're going to train one with 20 neurons, so split between 10 and 10 hidden layers. 2 hidden layers with 10 neurons each. To input 2 hidden layers into this type of a function, you just put C to create a list, and then you put the number of neurons in the first layer, number of neurons in the second layer. It doesn't have to be even. It doesn't have to scale in any direction, but it will make a difference, obviously, with the complexity. Well, it'll depend on the complexity of what you're trying to model, how much input data you have. Generally speaking, the bigger the network, the more training data you need in order to get good results from it. And you'll also find a couple of interesting error issues with, like we talked about on the whiteboard earlier on, where it's supposed to creep towards the minimum error. In some cases that doesn't happen, and it particularly doesn't happen when you have very, very large numbers of neurons in the hidden layer. So it's best to keep that as small as possible. Much like the other models that we've talked about, the simpler it is, the less likely something unexpected is to happen when you start using it in the wild, so to speak. So we've trained that second one. We're going to make some predictions using it. Then we're going to expand those predictions up again, and we'll plot them on a graph. And you can see that this actually looks a little bit better, right? There's definitely more of a positive correlation in there. We have some people going negative, some people going positive. That's sort of okay because we didn't give it any limits to the function. But I think you could approximately draw a line through there. So we've done a better job modeling the output with a more complicated network in this case. We could also have trained it for longer. We could have represented it with the same training data again. You have to be a little bit cautious about that because you can basically create a mirror for whatever your training data was and then have a model that doesn't generalize well. But that's one of the things that you want to look at as you evaluate these models here. Now, one of the other things we'll want to take a look at is using the same type of model for classification. So you'll remember when we talked through our first model, we set the linear output to true, which is going to give us a linear output, so there's no limits on what the number can be. If we wanted to predict whether a student would pass or fail, then we can set that to be false, which is going to give us the probability that a student passes. In this case, we don't have a pass variable set up in the data set, so I went ahead and created one. I said if you got 50%, you passed, because I'm very generous. And then I did something else. This is another little trick that I like to do. Whenever I create encoded variables like this, so I go 0 and then 1, I like to use a mean function on the column that I just created to make sure that it comes out with some sort of expected value, right? If I created this and then ran the mean of it, and all of a sudden I got a mean of 10, I'd know that I screwed something up. More likely than that, when you come through, you'll get a mean of 0, which means that it couldn't find any items in the list to fit this criteria, and it didn't actually encode everything. And I have embarrassingly made the mistake at earlier points in my career of working through something and tried to predict 0, and then been really annoyed and tweaked all sorts of model parameters and twisted this and changed that until I discovered finally that there was a typo in here, and I was actually predicting all zeros, so I had a perfect model on an imperfect target. So anyway, don't do what I do. And here again, we're going to recreate the keep variables column that has all the variables in it that we want to use in our training data. This is basically the same list, except we replaced the target, in this case, with pass instead of G3. And then we're going to recreate the training and test sets. I set the seed the same, so we're actually going to end up with the same examples in the training and test set in both cases. And then obviously we also have to recreate our formula because we have a new variable that we're trying to predict. If you remember, it's predict, squiggly line, all of the items that you want to use to predict it. And again, I just noted down here that this is what that formula returns. So if we look at my formula, you'll see that's just the same thing, but with the pass variable at the front instead of the G3 variable at the front. This time, as I said, we're going to set the neural network to output, or linear output to false, which is going to give us the probability that somebody passed. I just used 10 items in the hidden layer. Excuse me. In this case, so that trained very quickly, suspiciously quickly, I'd say. So let's take a look at the weights. Again, same thing as we had before. You have your 10 nodes in the hidden layer and all of their weights, all of the weights for each of the inputs. And then you have the one output node with weights for each of the connections to the nodes in the hidden layer. We can also plot this, and we'll get a graph that looks very, very similar to the one we had before. Some of the names have changed down here, but it's basically doing exactly the same thing. The only difference is that we placed extra constraints around the output node to make it predict a probability rather than predict a grade. All right, so we're also going to evaluate this one slightly differently, obviously. So we'll look at the predictions, create some predictions. Then we're just going to round them up to a 1 or a 0, and then we're going to look at them in a table with the actual passes and fails. So the table is really small. I hope you guys can see it. This gives us the zeros and the ones. So we predicted a 0. We predicted a 1 on the bottom row. They got a 0 in the left-hand column and got a 1 in the right-hand column. So there's 4 quadrants on this graph, right, when it comes to evaluating the model. 1 and 1 means that we predicted they would pass, and they passed, which is excellent. 0, 0 is what's called a true negative. Typo in there. Is a true negative. So we predicted they would fail, and they failed, which is bad for them, but good for us because we were correct. What we have in this this bottom left-hand corner is that we predicted a 1, so we predicted they pass, but they actually failed. And we have 18 of those. That means that because we thought the student would pass, right? Maybe we made certain decisions with that student, or with that, maybe we could have given them extra math tuition in this math class. Maybe we could have done something else or changed our approach in order to better help them, but we didn't because we thought they were going to pass. So there's potential consequences for ending up in that particular bucket, just as there are in the top bucket, right? The top bucket is false negatives. So that's this 0 line means we predicted they would fail, and they passed. So because we thought the student would fail, right? Maybe we put extra time into working with them, or we gave them extra homework, or we went and talked to their parents, or any other type of intervention. And that could mean that that was successful, or it could mean that maybe this is a student that had low odds of success, or we expected to struggle, but somehow managed to overcome that. And those in the real world all have different meanings, right? One of the ways in which this is used a lot is in terms of credit scoring, right? So if somebody's going to pay back a loan that they got or not pay back a loan that they got, and it might be that if somebody doesn't pay back a loan, our company that underwrites the loan loses a massive amount of money. So it's much more expensive for us as a company to predict somebody will pay back a loan and then have them not pay it back than it is for us to predict that somebody will not pay back a loan and then we miss out on the profit on that loan. So that's one of the things that we have to bear in mind when we're building this type of a classification model, is what really does this mean in terms of the output of the model. And in this case, right, it's somewhat academic, pun intended, where we're really looking at what factors could influence students to pass or fail a class, but there could be different costs associated with various errors within this matrix. And there's other ways to calculate that too. So the final network I want to train, and if anybody has any questions, you can start typing them because we're almost done. But the final network that I wanted to train is a ludicrously overly complex network in this particular case, with 40 neurons across 3 hidden layers. So we have 120 different neurons, and we're going to train all of those, and we're going to see whether that does a better job than our current one. That was also suspiciously quick. So this is the table of results from our first one. This is our second one. And you can see that. Oh, that's annoying. It did actually do slightly better this time. When I was playing around with this, I did set my seed and I've run things in slightly different order. When I was playing around with this network was significantly worse than the simpler network, which goes to show that having a more complicated network is not always better. Sometimes it overfits the training data and it gets so close and it mirrors the structure of the training data so well that it's basically useless as soon as you take it off the training data and try to predict anything else with it. This, in this case, is not significantly better. We did actually do quite a bit better job of separating the ones from the misses, as it were. But I'm not sure whether that will be enough accuracy for me to justify having this enormous number of neurons, because I wonder if we can plot this. Here, let's plot this network, and we'll see how much more complicated it is. It's going to take a second. So I'm not sure that little tiny weeny bit of accuracy justifies the additional complexity of what we've built here. So it's so big it doesn't even fit on the screen. So you can see, right, there's a lot more potential for error in here than there is in the smaller network, and it doesn't give us a significant benefit in terms of accuracy. And frankly, because it has so many neurons and our training data is so limited, right? This is all of our test cases, so this is 30% of our data that we put in this plot over here. There's not very many. There's a good chance that it's not trained very well and that this result is more luck than it is a good model. So that's something to think about as well. Whenever you consider adding layers or adding neurons, really think about the costs and the benefits in terms of complexity and the risk that you're taking with the output. That said, the final thing, neural networks are phenomenally powerful, but also can be a ginormous pain in the arse because they don't train all that well. They can be very finicky. If you don't give them the data in just the right way and it's not scaled properly, then they end up predicting all the same value or they end up doing something else stupid. So at the bottom of this code, there's a couple of things that are very common issues that you may run into. The first one is if all your predictions come out having the same value. That means that, well, the first thing to check is to make sure you're not trying to do a linear regression on a binary target like a 1 or a 0, and you're not trying to do or you're not trying to predict a probability when you have a linear target, which everybody's done, I'm sure. So check that linear output equals false. If you have variables with different ranges, as I said, that's one of the things that messed me up when I was looking through this data, is the number of absences was so much larger than everything else. It overpowered anything, but it didn't have much predictive power. So when you run it through with variables that have those wide ranges, you'll get numbers where everything's basically all the same. And then you can also play around with the number of nodes in the hidden layer. If you want to get adventurous, you can research what some of the other parameters in there mean with the learning rate, the step max, and things like that, and try and use those to overcome whatever limitations you have. The second thing is if you have a net that won't converge, you are frequently, one of the reasons it won't converge is because you're trying to predict a regression or a numeric target with a logistic output, or vice versa. So you're trying to predict a binary target with a linear output. So that's one thing to check. Again, make sure all the variables are scaled on similar ranges, and try playing around with the number of nodes in the hidden layer. And if you get brave, then play around with some of the other options in that function too. Those are the two pretty common scenarios that you run into with these type of networks. Once you can get one training and you have all the pipeline built, they're really fun to play around with and see how enormously complicated you can make them. Doesn't necessarily make a good model, but it gives you half an hour's worth of amusement as you train these things up to be as big as you can get them. So with that said, any questions or anything that you wanted to go to in more detail? That's good. I think I sent everybody to sleep. Cool. All right, so we got a couple of questions here. Something similar to a confusion matrix. Are you talking about these little things down here, Teresa? Because it is a confusion matrix. I used a table function to predict it or to create it, but it's exactly the same as a confusion matrix. In fact, it is a confusion matrix. It just doesn't use a confusion matrix function. It just uses a table function. All right, cool. The weight for each variable. So the weight for each variable, we're not going to do it with the last network because that'll be a pain and take forever to load. You want to use this $$ weights. So that's going to give you the weights for each node. Oh, I'm sorry. Were you talking about the ones with the label variables? I think that one's results.matrix. There you go. So results.matrix will give you the connections between each variable. So the intercept to first hidden layer, and it just gives you them in a list. The weights argument will give you that big matrix, which shows you spread out across a page what all of the weights are, and you have to sort of match up them with the names. But this one will give you what the weights are for all the names. There we go. All right. Yep, you can also use the confusion matrix function from the caret package if that makes it easier. Yeah, this is the confusion matrix is a pretty it's a pretty standard view of the output from a classification model, whether you have just a 1 or a 0 or more than that. So it's the confusion matrix is just a table. Packages like caret and some other model evaluation packages have a little extra information in there, et cetera, et cetera, et cetera. All right. We will post the presentation. I'll send all of this to Yelena once we're done, and then she can post them up along with the recording whenever the recording becomes available.
Yes, please. Send it to me.
So all of these details at the top are details about how the training was achieved. So the error is just a measure of the error. Reach threshold, I'm not 100% sure about. And then the steps is obviously the number of steps it took to get to that particular level. Here, let's try this. threshold, reach threshold, may be referencing there is an error threshold that all of these networks have when they train. So it might be referencing how well it hit that, how close it got to the error threshold, which would be when it stopped training, right? So whether it converged or not, basically. If it just continues going on and on and on and on and on, then that might be what it means. But I'm gonna have to look it up in the documentation and get back to you about that. That's a good question. The best practice on picking the number of nodes, the minimum that get you the accuracy you need without excessive amounts of training time or the minimum. You want the smallest number possible that actually fits the function in a way that you are comfortable with. The more nodes you have, the more complex the network is, obviously, which means two things. Number one, it means it takes a lot more computational power to run things through it and to continue to train it. So if you have a lot of nodes, it's going to take a lot longer to train. These are all really quick because they have minimal training data, but a lot of times when you want to train a big neural network, you need millions and millions and millions of rows, and you end up staring at a computer screen for hours and hours at a time waiting for it to run. So minimum number possible, and then obviously the more you have from a prediction perspective, the further out of sample you get, or the more the wider the range of your inputs, right? If you put in an input that it wasn't necessarily trained on, more complex networks might be more likely to give you a wacky result or an incorrect result when they are presented with new cases, just because, as with everything else, there's a greater potential for unforeseen errors the more complex the network is. So the error be less or more. The error should be lower. The accuracy should be higher. That's the way you should think about it. In this case, I would think that there's probably a lot of variance in the scores left to explain. So it doesn't surprise me that much that we only got 72%. You remember, right? This was what I considered the better model. Here, we'll move some stuff around here. So this model was what I considered the better model. This was on the worst one, so it wouldn't surprise me if we were like, what's that, 28% accurate with that, and 72% inaccurate. It depends on exactly how that error is calculated, which I'm not 100% sure on. For this particular model, I think you can specify it. So let's do this. I'm glad Pamela asked that question, because that's exactly where I was going with this. If we find the second one, so we're going to take this and we're going to copy it. And lost my second model. There it is. Put this in the comment. And then let's take a look at let's go look up to the top. It's going to take even longer because it's a bigger network. Was that it? There it is. Yeah, so in this case, I think the error is lower is better. That is traditionally the way you would talk about it, is that accuracy higher is better, error lower is better. I hesitate because in some R packages, that's not necessarily the way it's expressed. Because R is a lot of community, gets a lot of help from the community, and people build packages in their backyard, as it were. Sometimes error and accuracy get used in a more interchangeable way than we probably should. But yeah, lower is better for error and higher is better for accuracy. And in this case, to answer Pamela's question, right, we have better error on the second model. So the second model in this case is a better model, even though it's more more complex. So Wiley's asking about, aside from the range values, do we use any other parameters for feature selection? Feature selection with this you can do through any other, it's not something that we would do differently for neural networks than we do for any other type of model. A neural network doesn't necessarily have the same clear-cut, this is the most important features that things like decision trees do or random forests do. So one of the things that I've done before is that you actually build like a random forest or something like that, and then you use the most weighted features in there. There's also other methods of feature selection which you could use to try and determine which ones are the ones that you want to keep. And then there's usually a little bit of trial and error that comes in at the end too, with training it on different subsets of features. Excuse me, or trying to figure out which ones make the most sense. And in terms of standardizing, which is the other part of that question, right? Because we're not really selecting features when we change the ranges. We're just standardizing the ranges to make sure that they are similar and to make sure that no one particular feature is going to overpower any of the others. When it comes to that, the more similar they are, the better. If we wanted to do this in the really probably the proper way, as it were, we would go through all of the variables and give them a mean of 0 and a standard deviation of 1, just as we did with the age variable right here. So we divide by the, subtract the mean and then divide by the standard deviation. And there are packages in R that you can get that will do that for you. And they'll also store those variables, they'll store the mean and the standard deviation so that you can then get the standard values back if you want to expand them back out into their normal ranges afterwards. Here's the scale function that does that. Scale. Yeah, so the scale function will do that. Something to investigate for you. There we go. We'll make a note of it in there. Cool. Any other questions? Any other stuff that we wanted to talk through? Oops. Awesome. Well, thanks for giving me an hour and a bit of your Thursday evening. I hope to speak to you guys either via the discussion sections or emails. As always, reach out if you have any questions. Thanks, guys. Have a lovely evening.
Thank you, John. And go ahead when you get a chance, email me the code and then I'll post. Okay.
Yep, you bet.
Thank you so much. Let me stop the recording. Oops.